All right, let's look at how we can modify some of the discrete dynamical systems models that we looked at earlier in the course to incorporate randomness and use the computer to help us estimate probabilities of various outcomes. So for our example, we're going to look at, again, a generic difference equation, which has the form xn plus 1 equals some function of xn, where xn is our state variable. But rather than using some sort of deterministic update rule where we take the old state to calculate the new state, we're going to have some randomness incorporated into this function. And so we will not necessarily get the same outcomes each time. And to test this out, let's actually look at our rental car model, which I'll remind you, we had this nice little diagram here where we had cars in Orlando and Tampa, and originally we just said 60% of the cars in Orlando stay in Orlando and 40% go to Tampa. And then later we modified this to think of it as a Markov model. We said the probability that a given car stays in Orlando is 0.6 and 0.4 is the probability that it goes to Tampa. And now a third interpretation of this model is we could think of it as there is a 60% chance that each car stays in Orlando and a 40% chance that each car goes into Tampa. And we can start to think about, well, how many cars should we expect to have on each day, and what's the probability that the number of cars in Orlando exceeds a given number. And in particular, what we're going to look at is, suppose that you run this rental car agency, and your concern is that Orlando is a popular destination. You want to have enough vehicles there. You might want to determine what is the probability that I end up with less than 2,000 cars in Orlando on a given day, or less than 2,500 or some other number. Okay, now we know in the long run, on average, we expect that 3/7 of the cars will be in Orlando. And if we have 7,000 total cars, that would mean that we would expect the average outcome to be 3,000. But what if 3,000 is okay, but 2,900 is not enough? Can we compute probabilities like that? All right, so let's think about how we would do that. So I'm going to fire up Octave, and we'll first look at a simulation that is a little bit crude. So to summarize what's going on here, I've started my script with clearing all the old variables, that I like to start with a clean start. And then we've defined the parameters of the model. So we're going to do 10 steps, so 10 days we're going to simulate. We have our matrix that incorporates all of our probabilities. And I'm going to start with the initial condition that we used previously, which is that there are 5,000 cars in Orlando at the beginning and 2,000 in Tampa. And then we're going to use a loop to try to update the system. And so the way that we'll do this is we will we'll set up a matrix X, which is going to store the number of cars in Tampa and Orlando on day 0. And then for each day, we'll go through, and for each car, we'll flip a coin. And with probabilities that are given by the matrix we had before, we will either move those cars to Orlando and Tampa. So you'll notice down below, I've created variables called new O and new T. Those are going to represent the number of cars in Orlando and Tampa on the next day. And initially there's 0. And so we're going to go through for every car in Orlando, and then we will flip a coin. And if our coin comes up heads, we'll say the car is going to stay in Orlando. And in this particular scenario, it would make sense to assign a probability of 0.6 for that outcome. And then if that does not occur, then we'll say that the car goes to Tampa. And so we'll just increase the count for Orlando and Tampa for each of those cars. All right, so we're flipping one coin for each of the cars in Orlando, and then we could flip one coin for each of the cars in Tampa. The only difference is here that the probabilities of the final destinations are going to change. So there's a probability of 0.7 that you should stay in Tampa, and a probability of 0.3 that you should go to Orlando. Okay, so that means if we have 7,000 cars, for each day we're going to have to flip the coin 7,000 times, and based on the number of heads and tails, we'll get a new total for the number of cars in each location. We'll save that to our matrix in the next column, and then we'll rinse and repeat. So we'll just do that for 10 days. And if you do that, you run this, you might get a trajectory that looks something like this. As you'll notice, unlike our deterministic model, we don't get a nice smooth curve here. And that's because there are random fluctuations in the system. Sometimes you'll have a few more cars in Orlando than you expect. Sometimes you'll have a few less. But on average, you notice it does look like the blue curve is approaching something pretty close to 3,000, which was the fixed point that we found in our deterministic model. And the same thing with the red curve, it's pretty close to 4,000. Okay, so that's a process that we can use to simulate this, allowing for random fluctuations. But you'll notice that if you increase the number of cars in this model, it potentially could take quite a long time to do the simulation. Generating random numbers, a couple of random numbers is not a big deal. But when you start generating thousands or even millions of numbers, your program may take a little while to run. And so there is a shortcut to actually get to this sort of result more quickly, and it involves using a probability distribution that gives you the probability of getting, say, k heads out of n coin flips for a coin that has heads with probability p. All right, so let me show you how to do that. So the type of distribution is called a binomial distribution, and let me just show you what a histogram of its outcomes look like. So here, I'll show you the parameters first off. We're flipping a coin 20 times, and this is a fair coin, so we're going to give the probability of heads, assign the probability of heads to be 0.5. And so you'll notice that when you flip 20 coins, there are a few different outcomes. You can get 0 heads, 1 heads, 2 heads, 3 heads, all the way up to 20. And each time that we flip those coins, we could get different outcomes. Now, we could flip the coins individually, but mathematicians have looked at these sorts of probabilistic processes for many centuries, and so there actually is a nice closed form solution that you can write down for the probability distribution. And so instead of flipping individual coins, we can directly simulate this process of 20 coin flips and just go directly to the answer, which is the number of heads that came out. And you'll see that when I do this, in this case, the function in Octave is called bino RND. Bino is for binomial distribution, and RND for random. And the parameters we provide are the number of coin flips we want. In this case, we're doing 20 coin flips. The probability of heads that you want, which I'm using p equals 0.5. And then you can give the number of outcomes you want. And so I want a vector that has n experiments rows and 1 column. And the result will be I will get a list of, in this case, I have 1,000 experiments I want to do. So I'm going to get 1,000 outcomes of flipping 20 coins. And the outputs are going to be numbers, integers, for the number of heads. So I might get 10 heads, I might get 15. In fact, let's look at the first few. So if I just do results, I'll look at the first 20. Oops, I was calling it, head counts. You'll see that sometimes I got 7, 11, 10, 9, 13, various numbers of heads that came out, but they all seem to be clustered around the average value, which is if there's a 50% chance, you'd expect that on average you'd get around 10 heads. All right, and going back to the distribution, you'll see that we can actually see that there are certain outcomes that are not all that surprising here. Beyond just getting exactly 10 heads, if we got 9 or 11 or even 12 or 8 heads, that would not be particularly surprising because out of our 1,000 experiments, getting 8 heads happened somewhere around, over 150 times. Or between 100 and 150 rather. And the same thing with 12. So those aren't particularly surprising outcomes. But on the other hand, if you flip 20 coins and you were to get 18 heads, then that would be particularly surprising because that never happened in our 1,000 experiments. Okay? So we can use binomial random variables to simulate many, many coin flips, and you'll find that the implementation of this with the computer is much, much faster. So rather than having to flip 7,000 coins one by one, we can just flip 7,000 coins all at once, or 2,000, 5,000, whatever. And then once we've got that, we can use those numbers of heads to update our totals. All right, so let me show you what that looks like in the code. All right, so here is our modified program. So we've got we're initializing our parameters. We've got 10 steps we're going to do. We've got our matrix. We've got our initial condition. And then we're going to do this experiment 10 times, whereas you notice there was a little bit of a lag when we did it one time before. And in this case, I'm going to use this binomial random variable. I'm going to take the number of cars that are in Orlando, and the probability of going to Tampa is going to be A21, so it's the entry in row 2, column 1, 0.4. And so I'm going to flip a coin, and I'm going to say if I get heads, that corresponds to the car switching locations. And if I get tails, I'm going to say it means it stays in place. All right, so I'll do that for each car in our for the cars in Orlando. We'll flip that coin, and then this Bino RND will return the number of cars that should go from Orlando to Tampa. And then similarly, we can do the same thing for cars that are going from Tampa to Orlando, and then we will just update the totals accordingly. So I'll take the old value of cars in Orlando and Tampa, and then add up the changes. All right, and so we'll do this. And in this case, you can see I was very quickly able to do multiple experiments. And each one looks a little bit different, right? We didn't have exactly the same number of cars in each, but the nice thing about doing it this way is that we now get a sense of the distribution of different outcomes. So by doing multiple experiments, we can start to answer questions like, well, how long is it going to take before we have less than 2,000 cars in Orlando, say, or what's the probability that I have less than 2,000 cars? And now here I've only done it about 10 times, but if I did this 1,000 times, we could actually get pretty reliable estimates. And that would be a very useful thing if we want to quantify our risk. So again, if you think about yourself as the person running this rental car place, you want to make sure that there's a very, very low chance that you're ever going to run out of cars, or you're going to ever have too few cars. And so given that you think you need a certain number of cars, you could run this simulation 1,000 times and say, out of 1,000 experiments, I only had too few cars once. Well, if that's the case, then your probability of having too few cars is 1 out of 1,000, 0.001. And if that risk is deemed small enough for you, then you might be willing to continue as is. And if that risk is too high, then you might need to change the way that you go about your business. All right. So this example, I know we've kind of beaten the rental car example to death here in the sense of we've gone over it and seen it from many different perspectives. But what I hope it illustrates is that there are many different ways of thinking about modeling the same problem. We can model it deterministically, we can model it using a Markov chain, and we can model it using a Monte Carlo simulation. And each of those models have different pros and cons, and they have different things that they can reveal about the system of interest.